Hello, Algebra 2. Let's jump right into it. You are watching the video for 8.2. Thanks for joining. We're continuing to look at trig values, and we're looking at our special right triangles. We had a couple of lessons dedicated to this in geometry. We're going to do it all at once as opposed to splitting it up. We're going to look at 30, 60, 90 triangles and 45, 45, 90 triangles. So what do we remember about 30, 60, 90 triangles? Well, if you take an equilateral triangle and split it in half, you are creating a 30, 60, 90 triangle. And there's a lovely pattern that arises when it comes to a 30, 60, 90 triangle. The length of this side is k. The length of this side is k root 3. And the length of this side is 2k. What do I mean by that? Well, it's like a dilation, right? We can have a small 30, 60, 90 triangle. We can have a large 30, 60, 90 triangle. So this side could be length 1, making this root 3, and making this length 2. I'm replacing the k with a 1 and multiplying, right? So if k were 2, this would become 2 root 3, and this would become 2 times 2, which is 4. If k is equal to 3, this becomes 3 root 3, and this becomes 6. One more time, 4 root 3, and 8. Right? As the triangle gets bigger, the angles are staying the same, 30, 60, and 90, but the size of the triangle, the length of the sides, continues to get bigger as k gets bigger. But that pattern will always be true. What happens for a 45, 45, 90 triangle? When you take a square and split it in half, you're creating two different 45, 45, 90 triangles. So we know that these legs are the same length. They're both, let's call it, length k. And the hypotenuse is k root 2. That is the pattern that arises when we have a 45, 45, 90 triangle. Again, let's just play around with some numbers. Let's say the sides are 2. Well, then this becomes 2 root 2. Let's say the sides are 3. Well, then this becomes 3 root 2. Let's say the sides are 4. Well, this becomes 4 root 2. So you just gotta have these, what I like to call generic triangles, and then fill in the blanks as we look at these problems. So if we were to try to calculate sine of 30 here, sine of 30 degrees, what would we have? We would have opposite, which is k, over hypotenuse, which is 2k, and the answer would be 1/2, because the k's would cancel, and I'd be left with a half. So it doesn't matter what k is, right? It doesn't matter how big this triangle gets, whether k is 3, 4, 5, 6, or 7, the k's will always cancel, and your sine of 30 will always be 1/2. What happens for cosine of 30? Well, when you do adjacent over hypotenuse, that's k root 3 over 2k. The k's will cancel, and you end up with root 3 over 2. The k's will always cancel, and you will always end up with root 3 over 2. And tangent of 30 degrees, which is opposite over adjacent, is k over k root 3. We end up with 1 over root 3. However, you might recall something called rationalizing the denominator. Don't stress about this too much, but there's a rule in math that we don't like square roots in the denominator, so we rationalize by multiplying by the square root of 3 over the square root of 3. Why is that helpful? When you do a square root times itself, the radical goes away, and root 3 times 1 is root 3. That is how you will see tangent of 30 written out. You won't see 1 over root 3. you will see root 3 over 3. Some similar things happen when you do 60 degrees. I'm not going to write them all out. You can investigate that on your own. Sine of 60 degrees is root 3 over 2. Cosine of 60 degrees is 1/2. And tangent of 60 degrees is root 3. I'll go ahead and do sine, or the 45/45. Sine of 45 degrees is opposite k over over hypotenuse, which is k root 2. We get a similar situation where the k's cancel out and we're left with 1 over root 2. We multiply by root 2 over root 2. And why is that beneficial? We don't like square roots in the denominator, so when you take a square root times itself, the radical goes away, and root 2 times 1 is root 2. So sine of 45 degrees is root 2 over 2. The thing is, adjacent and opposite are the same here. So cosine of 45 degrees is actually the exact same thing. And when we do tangent of 45 degrees, as I just said, the opposite and adjacent sides are the same. So you end up with k over k, which is 1. I would encourage trying to memorize these. I would encourage trying to memorize them. Okay? What I see here is that for 30 degrees, the numbers get bigger, right? It goes 1/2, root 3 over 2, root 3 over 3, right? It's increasing. For 60 degrees, it's decreasing. The numbers are getting smaller in a way. It's not exactly perfect. I don't have like some perfect method to memorization, but try to find a pattern. Try to find a pattern that works for you. You can see here for 30 and 60, these guys are swapping, right? And for 45 degrees, these are the same. Find something that works for you. You don't have to have it perfectly memorized, but try to be 70% memorized so that way you're not always desperately having to look back, okay? So, also, let me not skip this question. What does it mean for sine and cosine to be cofunctions? I'm not going to write some fancy pants definition. Let's just explain this by example. Sine of 30 degrees is equal to cosine of 60 degrees, right? And sine of 60 degrees is equal to cosine of 30 degrees. That's what we mean by cofunctions. They sort of complement each other, right? 30 and 60 degrees are complements, right? They add to 90. Sine of 30 is the exact same thing as cosine of 60. They are complementary angles. So when we do sine of one but cosine of the other, they're equal. I could make up something totally crazy like sine of 20, just some random angle, is equal to cosine of 70. I can name an infinite amount. As long as these two numbers are complementary, their sine and cosine value will be the same. Cofunctions. All right, let's solve some examples. There's only this one page here of problems, right? So there's not a lot of variety here, and we're only at the 8-minute mark. So let's try to almost be done by the 15-minute mark. Let's see. And here's the start of some questions. Let me do one example though. So this is a 30, 60, 90 triangle. Remember to, it might help you to draw your picture here. This is k root 3, and 2k for a 30, 60, 90 triangle. I know I drew that kind of small, but hopefully, do I draw it again? Let me draw it again. So let me just draw it right here. Who cares? 60, 30, this is k root 3, and this is 2k. So what are we looking at here? This is the hypotenuse, right? This is 2k. 24 is 2k. So what does that make k? Hopefully you're saying to yourself 12, right? 2 times 12 gives me 24. Exactly. K is 12. So therefore the short side is 12 long, right? There's a short side, a long side, and a hypotenuse. The short side is 12, and the long side here is 12 root 3. That's it. That truly is it. It really can be that quick. And you can see how it's following this pattern. You double 12 to get 24, check, and you multiply k by root 3 to get the long side, 12 root 3. That's all that has to happen. Okay? So here's another one. Well, actually, let me make up one for you. Can I make up one for you? I know you're like, oh, great, now you're going to make the lesson even longer. Let me just make up another. Holy cow, did you see that? Let me make up another one for you. And what if I told you that this side is 9 root 3? That side is 9 root 3. I want you to tell me what is x and what is y. So think through that for a second. It ought to come pretty quickly to you. What is x and what is y? A question's popping up on screen. So if it's following the pattern and this is 9 root 3, then therefore this is 9. And then you double this to get the hypotenuse. That becomes 18. It really, truly is that quick. Now, why did I just make that example up and not have you do B? Well, B has got a slight twist to it, okay? B has a slight twist to it. The hypotenuse is k root 3, right? This hypotenuse is k root 3. But, or sorry, not hypotenuse, the long leg. This is the hypotenuse. The long leg is k root 3. That just says 8. So have we broken the pattern? Have we broken the pattern? No. K is just not a whole number. K can be anything. K doesn't have to be 2, 3, 4, 5, 6. K can be 7.5. K can be 5 over 4. K can be 2.34567. It literally can be anything. So K here is just not a whole number. But nonetheless, 8 is equal to k root 3. Okay? We know that to be true. We know that the long leg is always k root 3. Let's solve for k. Divide away the root 3, and you end up with 8 over root 3. Now, as we said before, we don't really like square roots in the denominator. So if you multiply by root 3 over root 3, the root 3's cancel, and you're left with 3, and the numerator is 8 root 3. So x here is 8 root 3 over 3. Okay? You still double it to get the hypotenuse. You still double it to get the hypotenuse. So when I double 8 root 3 over 3, I end up with 16 root 3 over 3 for y. I know it looks messier, but it's still following the pattern. It is still following the pattern. And here, let me open up a calculator for you real quick. I don't mean to make this lesson longer. We're already at the 13-minute mark. I love how I lied and said that maybe we would be at the 15 mark. If I take that messy fraction, 8 root 3, divided by 3, it gives me 4.61 blah, blah, blah. Right? That is, whoops, sorry, I meant to switch. Sorry. That is this fraction right here, the short side. If I take the short side and multiply it by root 3, it should give me 8. Right? Because if this is k, I simply multiply by root 3, and it gives me 8. Check it out. Let me switch over. If I take this and multiply by root 3, it gives me 8. That messy fraction when multiplied by root 3 simply equals 8, and that's what we wanted. Okay? Hopefully I'm making sense there. We'll see it again here in a sec. So here is a 45, 45, 90 triangle. What do we know about 45, 45, 90 triangles? We know the legs are the same, and then the hypotenuse is k root 2. So if this is 9, boom, that's 9. And if they're both 9, then y is equal to 9 root 2. When k is a whole number, it's so easy to see the pattern. But when k is not a whole number, we run into trouble, right? It's just a little bit more of a hiccup. So let's look at example D. We know that the hypotenuse is k root 2. Okay? We know that the hypotenuse is k root 2. I'm still going to divide by root 2 here to cancel that out. So k equals 5 over root 2. Oh, sorry, no it doesn't. 5 divided by root 2. I need to multiply by root 2 over root 2 to cancel out the root, and I end up with 5 root 2 over 2. It's always going to fit a pattern like that. You see how this one was 8 root 3 over 3? Well, this is 5 root 2 over 2. You're going to see that pattern arise over and over, and you might be able to skip to the final answer. So k is 5 root 2 over 2. 5 root 2 over 2, 5 root 2 over 2. So the legs are a weird length, and the hypotenuse is a whole number. So it's still following the pattern. It's still following the pattern. This is the same as this. They might be messy looking, but they're still following the pattern. And if you take this and multiply it by root 2, just as the formula says, right? Just as the drawing I have there says, if I take 5 root 2 divided by 2 and then multiply it by root 2, boom, it gives me 5. So we are still satisfying the pattern. Okay. We're still going to be able to make it short here. Use your special arc triangles to find the following trig values. Just look at the table. Just look at the table. Sine, I know it's kind of teeny now for you, but I'm looking at the table and I'm filling it in. Sine of 45 degrees, root 2 over 2. Cosine of 30, do you know it? Do you not know it? Look at the table. Cosine of 30 is root 3 over 2. Tangent of 60, do you know it or not know it? Tangent of 60, it's up there. It's root 3. Here's a question for you. Make sure you're still listening. What's tangent of 45 degrees? Do you know it or not know it? Look at the table. Tangent of 45 degrees is, question pops up on screen. You just saw it on the table. I just scrolled up to it. Hopefully your eyes were open. The answer, 1. And then let's end it here. Find the cofunction. As I said, the angles must be complementary in order to be cofunctions. So sine of 45 degrees is equal to cosine of 45 degrees because 45 plus 45 is 90. Cosine of 30 degrees is the same as sine of 60 degrees. 30 plus 60 makes 90. Sine of 32 degrees is equal to cosine of 58 degrees because 32 plus 58 is 90. One's cosine, what is sine, right? Cosine of 30 is not equal to cosine of 60, okay? We're having to switch functions. So give me the last one, and we're done with the notes here. Cosine of 75 degrees is equal to sine of what angle? Question popping up on screen. Sine of 15 degrees. Thank you very much for watching. I would encourage looking back at these 4 examples if I went a little too quickly or if something wasn't clicking for you, right? I have a feeling that the table is probably self-explanatory, but actually filling in the triangle might be giving you a little bit of trouble. That tends to be the most difficult thing in geometry. It might be the most difficult thing for you now. So I encourage you to watch back those 7 or so minutes if you need any additional help. You can also Google 30, 60, 90 triangles and 45, 45, 90 triangles, and you will see potentially a gajillion examples. So thank you for watching. I'll see you in class, and enjoy the rest of your day, weekend, whenever it is that you're watching this.